of all the greenhouse gas emissions from the last work we have. But I just want to take a peek. Agriculture is 10%. Industrial outputs, almost another quarter. Commercial and residential building space is another 12%. And I think for us, we attack each one of these sections because I think we have something to offer in almost every area. Not so much electricity generation until the conversation comes around decentralized power. But when we're talking about reducing greenhouse gas emissions, certainly a big win is in transportation, but I would argue there are also significant opportunities in each of those segments. And we'll talk about those in another time, but not today. All right. For me to be believable to this group, and I'm the first to admit, you're working on hydrogen. You're working on a lot of solar, wind applications. You have to work with me on only two areas. One, fuels aren't binary. No matter what people tell you, they're not binary. They're not just clean or dirty. They range in the spectrum from very clean to very dirty. I would say solar, wind, hydro, pretty clean. I tend to say coal, oil, wood, pretty dirty. I think propane and natural gas would be on the cleaner end of the spectrum. And again, when I talk like this sometimes, I really don't want people to think that I'm a shill for the oil industry, because you really won't hear me advocate much for gasoline or diesel fuel as a clean fuel. The consumption and burning of diesel, the storing of diesel is inherently dirty. And anything that has made it more clean is technology, storage, but it is inherently dirty, where I would argue, as you would too, solar, wind, hydro, inherently clean. And so you have to agree with me that we should get rid of the dirty fuels. We want more of the clean fuels, but we probably are not in a position to rid ourselves of natural gas or propane. I think that's one key point that you have to agree with me on. The second would be that in order to be really scientific about whether a fuel is clean or dirty, we really need to talk about the full fuel cycle. We really need to think about its analytics and its contributions and its wastes from the whole spectrum. Everywhere I go, even intelligent scientists will often talk about things being emission free. They're not. They might be emission free if the conversation is just around site energy. But if the conversation is about what does it take to make that, to power it, and what do we have left over when we're finished with it, then that's really what I guess most languages would refer to it as full fuel cycle. Cradle to grave, you hear a lot of people slang it, but that's the only way I think you can evaluate any technologies. I was not terribly long ago in Amsterdam and working with the ports there, and in their view, hydrogen is the fuel of the future, but not gray hydrogen, green hydrogen. They don't want any part of gray hydrogen. And it's interesting, as you think about, I think, the full fuel cycle, I really question sometimes how feasible some of that is. Now, you'll see some notes that we have at the bottom that on units of energy, to get 1 unit of propane consumed takes 1.15 units of raw energy, where electric is almost 3. Those numbers can be all over the map depending on what you're talking about, but it generally relates to the fact that a centralized power plant, maybe it's 40% efficient, maybe if it's really efficient, it's 50%, line losses. That's how you get there. But for any technology, and I love talking to scientists because I think scientists are much more intellectually honest about that, you cannot just talk about one component of the production. You have to talk about all production. So if we marry those two concepts, fuels aren't binary, and the fact that I want to talk about full fuel cycle, I really think we have something to offer. And I'm always willing to have a discussion. When we have talked in the past about what was important to us as we think about propane fueled vehicles, we've generally only really talked about range, payload, and cost per mile. For 20 years, that's what's been important. Will this vehicle give me a couple hundred miles of range? Will it pull my 30,000 pound payload, my 40-ton payload, whatever it is that a truck, because I'm not talking about passenger cars. You'll never hear us advocate for propane or natural gas fueled passenger cars. We tend to think that's probably going to be electric, or maybe one day in a different lifetime, a hydrogen or fuel cells or something. We're talking about vehicles where range and payload matter. Just in the last 4 to 5 years, really have fleets started talking to us about emissions. And now, I would argue, in some fleets, emissions and sustainability trumps range, payload, or cost, assuming that the fuel does meet the requirements for the fleet. That tends to be where we work. If a fleet needs to go 250 miles in a typical day, they're not going to choose electricity today. Very few applications give them enough battery range to have that kind of a distance through cold weather, through warm weather, through unanticipated things. So we have just started talking about that. I wanted to show you all a couple different products that we've put out there. This actually is a bus that runs in the national park system. Today, that bus is running in Acadia National Park. Big commitment to propane fueled vehicles for a long time. It's relatively cold there in the winter, but in the summer, they really don't want cars in the park. So we actually custom built this bus, put it on propane for them. And this is the model of the future for us into the national parks and into lighter duty transit systems. I could talk to you at length about the emissions, and I will probably at the conclusion of this, but it's a really modern product for us featuring a Ford engine. Paratransit has been a huge product for us. Again, I talked about range and payload. Paratransit doesn't really know at the beginning of the day what their total range is going to be. They tend to work on a demand loading. Maybe some of you have studied paratransit. Most of these are subsidized routes, subsidized by the community. So cost is really important. And a lot of paratransit fleets have gone to propane fueled engines because they can get the range they want, they get the payload they need, they get the cost they need, and in most of these applications, we're cutting emissions 50% from gasoline or diesel. We'll talk about that specifically in a bit. I see this vehicle everywhere I go. I assume you do in California as well. This Nestle water, you need to work on your image when you sell bottled water. So one of the ways Nestle does that is by being a little bit more considerate of the fuel in the trucks. Big commitment to propane. They needed range, they needed payload, but they needed to enhance their image. And they're quick to tell you how many tons of different criteria pollutants they save in going away from diesel to propane. UPS would be the last kind of a marquee customer. They don't really have a concern about payload, but they do have some concerns about range, and they have a real interest in their sustainability scores. Probably of all the fleets we work with, probably the most conscious of their brand and its impact on environmental matters, and a big commitment. Now, also a big commitment to EV, a fairly big commitment to LNG, somewhat committed to compressed natural gas. So a favorite fleet for us because it's a good reminder that probably one size doesn't fit all. Most of these fleets and most of the progressive national fleets are running a variety of fuels. It just happens that in many cases, propane has been a fuel that has really worked well for UPS, and California has been a very specific target for them running this type of package van. So you didn't see me talk about tractor trailers. You don't hear me talking about trains. We really have not played in high horsepower applications. But I put a picture of the ship up just to kind of remind me and talk with you for a second that it's not that we're afraid of horsepower or torque. This ship and 15 or 20 others like it today running on propane. Maybe some of you who study closer to the fuels and fuel standards know about the changes in the maritime fuels to get away from that heavy bunker they were doing. And I chair the innovation group on a worldwide scale. And I had said 7 years ago that we wouldn't see this, that we would not see LPG fueled ships. So I get about an email every week from one of the engine makers whenever they book another propane fuel engine for a ship. They send me a good-natured email just to remind me how wrong I was, because in fact we see, at least in a lot of the niches, ships that aren't bunkering routinely in Hong Kong or Singapore um, can bunker propane in other places, and we see them move. So the point of this is, you don't see a lot of action in the US with us in real high horsepower applications, and we haven't pursued Class 8. It's been a financial thing more than a technology thing. But I do think over the next couple of years, and you'll see why, we'll kind of go backwards now from these horsepower and torques and move into road tractors as well. If we hadn't done anything, parts of the technology, I know this isn't a mechanical engineering class and I'm not going to make it one, but part of the technology of engines is just benefiting us. So without any of the investments, and we tend to act like a venture capitalist as well in investing our money in many of the projects you'll see me talk about, but all of these technologies are coming to make gasoline and generally diesel more friendly. Direct injection, turbocharged, changing the compression ratios. California leads the way and is the primary driver between either low NOx or ultra low NOx. I'll talk about that in a bit. But those technologies help gasoline, but they also help us. And if we had talked about technology even last year, I wouldn't show these two engines. These are both 2020 model engines, just come out, cleaner, more powerful, more efficient than the engines they replaced, and kind of the workhorse for us. But this is the engine that we would stake our future on. And this is the engine and the engine concepts of why I think in a zero carbon world, or at least a low carbon world, we have a place to fulfill. Because with this Cummins engine, this was taken from a diesel block. This actually happens to be the 6.7. We used about 70% of the conventional diesel parts, but we built a whole new top end for this engine to introduce the propane, change the compression ratio. And what we've gotten out of that is power and torque that now is unlike anything the diesel world has seen. I omitted the torque curves from this, be happy to share them with you later if anybody really wanted it. But this engine is more powerful and now achieves the thermal efficiency of a diesel engine. That's never been done before, to take a non-diesel fuel and make the thermal efficiency. That's the chart you see on your right. That, you know, the typical diesel efficiencies are in blue. The green are our propane engines, and you see that we're at the same, or in some cases, depending on if we really kind of go to an auto cycle, that we may actually even have a little enhanced efficiency over a diesel engine. Probably for us, when the conversation's around emissions, though, we get really excited about the chart to the left. This engine, and again, I don't expect most of you in this class to be in the certification of engines, but if you did certify engines, you would recognize that number in the middle green bar at 454, which is significantly lower than any diesel engine we're working with today. and significantly, meaning 25% lower than our next best engine in the propane world. Really important because, as we'll talk about, our Achilles heel for emissions has been CO2, greenhouse gas. And the way we get there is by making changes in the fuel and making changes in the technology. But it's this kind of technology that people don't generally give us credit for. And I think as we think about a path to zero, all of us agree that hydrogen in the future won't be quite like hydrogen today. I tend to think that the electric vehicles of tomorrow won't look anything like an electric vehicle of today. The battery technology will be completely different. Perhaps energy storage in general will be completely different. Solar cells will be more effective. All of that electric challenge that faces the market today, I think will have some technology solutions. But what people tend to discount is that some of these low carbon solutions will also have technology ride to their rescue and make them look fundamentally different than they look today. The work we've done with CUMMINS, the engine, that's not just a concept. This is an engine that's built, tested, being driven today in trucks on the road as we just put them through their paces to confirm durability and to confirm all of the parameters in the real world that we've seen in the lab. But I think it's a key function for us as we look forward to know that our technology can keep pace. Lots of other tricks we've done. If you rode in a cab in Las Vegas, highly likely it was propane powered and a hybrid technology. Several thousand cabs like this operate on propane. We have a lot of operating data. Had there been the Olympics in Japan, this was the official car of the Olympics. It's a factory-built Toyota that happens to have a propane engine and a hybrid electric drive system. That was the official car of the Olympics, and I assume it still will be when the Olympics happen in 2021. Future, no different. Although we'll start improving on some other things, we'll have more DI, we'll be more higher boosted, and we'll start fooling with some technologies that many of you have in your car today. Start stop. When you pull up to a brake, to a stoplight, your engine cuts off. Some of you, actually my vehicle has cylinder deactivation, so if I only need 4 cylinders, it runs on that. All of that even just changes our technology going forward. And all of that is just with conventional propane. We have worked for some time to develop a renewable component. I want to talk about that for just a moment. And I know this is an area of interest for Colin, but also hopefully it's an interest for many of you. When we set about trying to understand renewable product, even what we thought a renewable product should look like, we went about it, I think, differently, because we were committed to find a renewable product that obviously had a low carbon intensity. That's what you're using it for. But we wanted one that had an inexpensive feedstock. If it was going to be inexpensive, that meant it was going to be abundant. We wanted it to have a relatively low energy conversion. I still tend to think that American or engineers are not going to waste BTUs. And so we're not going to allow something that takes 10 BTUs of even renewable energy to make 1 BTU of energy. You may not agree with that premise, but I don't see anywhere in the history of time that we have really wasted energy. It's too expensive and difficult to make and store. And so we thought a low energy conversion would be very necessary, relatively efficient to get it from what it is to renewable product. And finally, we wanted that product to be priced competitively. So today, we actually have done that, taking in a biodiesel refinery that's using fats and oils as the feedstock. We're able to go into that facility, and before they get to renewable diesel, they have made renewable propane. that renewable propane could have a carbon intensity as low as 11. Um, California right now has assigned it generally, I think, a 36, and that may be off by 1 or 2 points. And that's mainly because of the transportation from where we make it to where we're using it. But what you can see, conventional propane, California assigns us an 83. Most places, it's a 78 or so. Renewable propane, depending on the feedstock, can range from really low teens to almost 60. And now we're starting to play with blends. One of the interesting things that's happened in California is California has assigned dimethyl ether. That's a kind of a drop-in, if you will, for diesel fuel. It can be made from a lot of products, but when it's made from dairy waste, they assigned it a carbon intensity of minus 273, I think. And so if we take a 20% blend, which is quite easy to do, DME and propane play very nicely together. We can take a 20% mixture, our carbon intensity all of a sudden becomes 0. So you will continue to see us innovate not only in conventional propane, but renewable propane and then renewable blends. And when I speak about this work is going on across the world. Europe is quite a bit ahead of us in their commitment to renewable propane and renewable blends. And we tend to share a lot of that research back and forth. But frankly, California right now is leading a worldwide study as we blend propane, and renewable DME in different truck engines and run them in tests just to see not only how they perform, but what our emissions components are. All right, I'm just going to mention infrastructure because I don't usually talk about it. And when I do, people seem to ask a lot of questions. That's a very typical station for us. Above ground storage, but if that tank were to leak, it's not going to pollute the groundwater or the soil. Kind of a modern dispenser. Fleets like that because if they add more trucks, they can add a tank. If they add a lot more trucks, they build a bigger tank. If they move their facility, they pick it up and take it with them. And the electric demands are really simple. Generally 223 phase and about the lowest power consumption because propane moves around in that system. We move it around as a liquid. And in an engine, modern engine, we tend to burn it today as a liquid, but very typical system. And just kind of show the level of thought that goes into it. This nozzle would behave almost like a gasoline nozzle to you. It didn't really exist 10, 12 years ago. We went around the world and we got the world to agree on the best technology. And most everywhere in the world, except for a few parts of Asia, have centered on this nozzle, emission free, or at least somewhere in the 0.02 cc's per use. So virtually emission free, work perfectly, and it's kind of the hallmark of us. Because I think, again, we have been around long enough to see that your system has to be relatively complete. And if you have a low emission engine, but a completely high emission fueling system, you've negated, what you're trying to do. And I think it's a good tangible piece for us that we're very comfortable about our systems. Okay, so let's talk about our path to 0. And as I said earlier, I like to talk about 3 sets of emissions. And I'm a firm believer. I'm not a scientist at all. I'm an engineer that's been around business and investments way too long. But I talk to a lot of scientists. I fool with a lot of children as we work on school buses. And I talk with a lot of school doctors and community physicians. And I personally believe that particulate matter and NOx are the real current health hazards. I suspect in California, you see it too. So let's start talking about particulate matter. Our most modern engines, I have to say it's virtually zero because we know there's some particulate matter there. We really can't weigh it. We can't really see the particle sizing. Um, it is essentially gone. And if we use renewable propane, particulate matter is literally zero. So and as I grade ourselves, I tend to grade us with a check plus. NOx. That's the next. That's the next thing. Again, if you're a true Californian, you're well versed in NOx, and anybody that's listening from the faculty, it's a lot of work that they do here as they work with the agricultural community, the transportation community, so many ways to reduce NOx. But I'm quick to say here that propane with a simple three-way catalyst has reduced NOx 96% from the best-in-class diesel. And I've seen this study a few places. We confirmed the work. Our best-in-class engines certified to that NOx standard, the ultra-low NOx standard of 0.02. It operates at half of that all the way through the duty cycle using a three-way catalyst. A modern diesel engine that is very efficient on a highway at highway speeds and high temperatures, high heat, high load, but in stop and go delivery, such as perhaps a package delivery in your neighborhood, a diesel school bus stopping and picking up children, they may be 6 to 8 times their certification level for actual NOx emissions. I've seen that work confirmed now in 3 separate studies, 2 in the US and 1 in Europe. And our vehicles certified 0.02 and operated half of that over the full duty cycle. Big check for us. Greenhouse gases, that had been our problem. Now, this is one fundamental part where propane is better than natural gas. Historically, what I've said about natural gas or propane tends to apply for natural gas, particularly for buildings or farms or things that aren't necessarily engines. Propane and natural gas have one very strong thing not in common. The global warming potential of unburned propane is about 4. If you go to your local grocery and you wander into an Aldi or a Lidl, the refrigeration cabinets there are propane. They don't call it that. They call it, they have its own Freon or its own refrigeration number, R290, but that's propane. It's because unburned propane is a really great at low global warming potential. It's a good start. It's nothing but a good start. The rest of it is how do we handle it in an engine, and we have to handle it in by being very efficient. And we've done that in this new class of engines, and we'll keep getting better. So that's where I give us a check minus. I wanted to finish with 2 things, and one I think is probably super more relevant today than it was 3 months ago. It's always been relevant. It's always been a key issue to me, but that's the concept of environmental justice. Historically, people use that in a broad context when they talk about placing a power plant perhaps closer to the neighborhoods where people are least likely able to oppose it. Perhaps a pipeline. Maybe it's a power line. Maybe it's a power line from a solar field going to where people live or historically routed where people are least able to complain about it. Environmental justice is used sometimes that government comes out with great incentive plans for electric cars, and that's most often used for people who are able to buy their Teslas. And generally implies that the higher socioeconomic people who need that boost the less benefit the most. I think for us, COVID-19 has really proven the last piece of that, and that is in order to achieve clean air, clean water, it generally is going to either take current technology that's very clean, being used more, or it's going to take massive government investment to get to an electric system that really can promote completely, almost near 100% renewable power? What's the investment we need to make with hydrogen to come up with a truly hydrogen economy? And I think for us, for propane, one of the things, again, in our niche, not for everybody everywhere, but particularly as a transportation, for vehicles where payload, range, cost, and environmental matter, then who's going to pay? And I think pre-COVID-19, we felt all that the government would invest in this. Government has to invest. If you think about the Paris Accord, um, we're not even at the standards of the Paris Accord today while everybody is at home. I saw those numbers just the last couple of days, and I'm sure they'll vary a bit, but who's going to pay? And now that the government has paid, round numbers, we're nudging $3 trillion of investment around COVID-19 for social programs. Where is that money going to come from to now go to the next level of environmental investment? I think that's again a place where really clean vehicles, like propane fueled vehicles, perhaps natural gas fueled vehicles, will play in, because we can do that with no government intervention, compared to what it takes, I think, to move modern batteries to where they need to go, to move the electric grid to where it has to go. It's a strong argument for clean fuels like propane, particularly post COVID-19. So I want to finish by this picture. And I know I spoke at a transportation conference not long ago, not right before we kind of all stopped traveling and working. And I was a little bit fearful of going to a transportation conference with a slide of a school bus. Before I even got to the podium, and I was an early speaker in the conference, a school bus had been mentioned 3 times. But this is implied to me where the future is going. This has shown me where the future can be. And so I want to tell that story for a second, because this is something that I've been a part of really ever since I've been in the industry. Because a forward-thinking school superintendent about 12 years ago saw that the children waiting to pick up the school bus in the bus line, their faces were about the same level as the tailpipe. And he could tell what the diesel smoke was. Diesel exhaust, the visible part is clearly particulate matter, lots of other bad things, as you would know. He went on the bus and he smelled that the bus didn't have air conditioning. So the students on the bus were breathing the same thing that the students were experiencing in the bus loop. And he said, we need better. We owe it to these children to do better. We built a propane bus. We built it because it was going to be cleaner, in one emission, particulate matter. Once we had a couple thousand buses running, then all of a sudden we saw that these buses cost 50% of the cost to operate a diesel bus. And school systems first talked about how much money they were saving, but then lately they started talking about what they were doing with the money. In fact, we commissioned a study by an independent agency, and they said if we converted all the diesel buses in the country to propane, we'd save enough money on the fuel and maintenance to hire 23,000 new teachers into the classroom. Atlanta, that school system, heavy commitment to propane buses. They started paying all their drivers with the money they were saving, completely changed the fact that they couldn't attract drivers anymore. And everywhere I go, school systems tell me I bought computers. I was able to buy better football helmets. We fixed a leaking roof, whatever. When a school system saves money, it's crazy important. Now, here's the final piece of this. Georgia State did a study, and they said children that ride to school in low emission buses are testing higher in math and science. Sounds crazy, right? Sounds nearly impossible. I thought the same thing when I first saw the study, although the study has been looked at by several agencies, Brookings Institute to be one, and said, no, this is a scientifically complete study. And the truth is, children that ride to school in a low emission bus generally attend school more days. than children who don't. Childhood asthma, days off, seem to be a real problem for young lungs. These buses have reduced particulate matter, reduced NOx emissions, they're quieter, and teachers tell me routinely the children come to school calmer, they get into learning mode faster. So it's really only logical that they learn more, learn better. Now let's talk about the drivers, because I hear this as well. The drivers talk about no longer having headaches from being with diesel all day, perhaps no longer have breathing issues themselves. Drivers much prefer this. And I think that is the future that I see for clean transportation. We've gone away from diesel. We've gone to a quiet fuel, a cleaner fuel, a cheaper fuel. And I think that is the future for clean transportation. One fuel, one idea for the future. So I'm going to stop there. I'm going to put up my information, and then I'm happy to kind of take questions or have a conversation, or Colin, however you want to proceed.
Sure. All right. So thank you, Tucker, for the presentation, and thank you, everyone. Had a couple questions in, some of which I think got answered during your presentation. The one question which is my question. I'm gonna insert it the first and sort of take the prerogative as moderator. So I definitely appreciate all the things you said about the role of propane in the pathway to zero. It seemed like in a lot of cases, the key ingredient was renewable natural gas, and you mentioned the sort of very negative RNG scores that some sources of RNG get under California's low carbon fuel standard. So that all of the negative sources get because of the avoided methane credit, which is perfectly legitimate science, and they deserve that negative score, but that negative score won't last forever. It only exists as long as that avoided methane is additional to whatever other policies are out there. And so, as California has already adopted policies in the next about 5 years, requiring all those methane sources to go away, all of those RNG scores kind of go from being really negative to, they're still a low carbon fuel. They're still down in like the 30s or 40s right. of CI, but not as low. Is there an alternative pathway for renewable propane to get back to zero without having that really big contribution from the negative CI renewable natural gas?
Yeah, so I mean, I love the question. Thank you, because I think for all of us who really ultimately want to become practitioners of clean air, clean water, clean cities, clean communities, you want to get there because it's really clean, not because policymakers, lawyers, if you will, game the system to a degree. And so the first thing, let's talk about conventional propane. Conventional propane doesn't have that interaction with the environment like unburned methane. Huge piece. And I think one of the things we wrestle with every day is how to talk about it. Is propane is in fact the byproduct. It's a byproduct of either making gasoline, but really realistically it's a byproduct of cleaning up natural gas. And how do we treat it? Do we treat it as it was what we were looking for and therefore has all, carries the full burden, if you will, or do we treat it as it's a byproduct, a waste product, and perhaps treat it a bit differently? And when we really move the reality of the science into the models, California GREET model to be one, and a lot of the renewable fuel standards, the research is still fresh, but we see the contributions from conventional propane are lower than we have thought, and the contributions from renewable propane, not renewable natural gas, but renewable propane can also be much lower. For renewable propane, though, I would say we don't really think the long-term future will be from fats and oils. We think it has to be from waste agricultural products, some kind of biomass, and that's what we're working on worldwide right now. I will say, just while you're on the subject, one of the more exciting things I'm working on right now is the concept of carbon capture in our vehicles. And while I'm certainly not prepared to say we have ironed it all out, the concept of actually achieving carbon capture seems to be inside the realm of solid technology and engineering. So we're very excited about it. But to your point, I tend to want to work first on affecting the reality of the A-fleet model and the California models, because most of them don't even really treat propane for what it is. They tend to treat it using the gasoline factors, and that's not right. We know far more about it. As we move to the renewable propane, and not from natural gas, renewable propane from a bunch of biomass sources, I think you'll see those carbon scores come way down.
All right. And then one other question that was asked by a student was, do you have a general like number for the propane leakage rate in the transportation sector? I know we've got a lot of students here who are working on various models of energy systems. And so even though it doesn't have a huge greenhouse gas impact, knowing the leakage rate just from sort of like an energy balance impact becomes important.
Yeah, so actually we don't. That's actually a number we're trying to get. Our pressures are much lower than natural gas. So I mean, I study those numbers a bit for natural gas, and we would be pretty sure. First off, most of our pipelines are flowing more liquid than gas. It's kind of an interesting phase solution propane can be, but generally most of the pipelines are liquid rather than vapor. So much lower than natural gas, but no, we don't have a number yet. It's funny, I watch the natural gas guys fight all those numbers. I would say we realistically could be 1/10 the number for natural gas, and that is a number we're starting to study, but it is not known right yet.
Okay. Were there any other questions from students? Everything that I've gotten so far has been answered in one way or another. Give people a moment. All right, well, I'm not seeing anything and we are getting pretty close to 3 o'clock. So I think I will probably wrap things up here. So first of all, I'd like to very much thank you, Tucker, for taking the time and hanging with us through the technical difficulties. We are still getting used to this new method of operation. Thank you for the students for coming in and giving us your time and attention, and for the questions that came in. Also, definitely thank you to Anne-Marie and Miriam for a ton of work in getting this all put together and resolving all the technical hiccups that came along at the start. For all the students who are on here, the information is going to be posted with the recording of the video. So you have Tucker's information here, and feel free to reach out to him if you have any specific questions about propane or any of the things that came in this video. Anne-Marie, do you recall who the next week's talk was going to be from? As she frantically tries to find the mute button again.
Yeah, I don't off the top of my head, but it's posted on our website under outreach seminars.
Okay. All right, well then thank you all again, and hope you have a good afternoon and weekend.
Thank you, Colin. Thank you, everyone.
Right. Thank you.
Thank you.
Bye now.
Thanks, guys.
Thank you.
See you next week.